Now, how do we find the flexural capacity? So, now that we have got the steps involved in moment distribution method using equivalent frame method. So, we have seen first we are finding out the moment distribution. So, at the end of the day we want to find out what is the distribution of moment along the frame, right. Then at each cross section we are going to make sure that these are your demand, okay, and these are your capacities. Okay. So, in IS code we say that as MR moment resistance at ultimate MUR, right. So, or we can write this. So, AC code we write that as a nominal capacity with some reduction factor. So, let us say MUR. So, MUR the resistance has to be greater than your demand, right. Then the design flexural strength is calculated by sectional analysis assuming ultimate strain conditions that we have already seen, right. How to use the for flexure ultimate analysis we know. Then the distribution of moments across the width of the design strip is typically not considered, because post tension slabs you have PT cable throughout the width. So, every region is considered to be equally stiff, but in a typical RC slab what we do is we also do the transverse distribution of the moment, but here we do not do that. The reason is because they are all pre-stressed, they are not cracked. So, it is assumed that along the perpendicular direction, along the width of the strip, the stiffness is not going to vary significantly, right. So, in this way we can check at different cross sections to ensure that whatever the PT cable that we have, whether it is able to take care of the ultimate strength or not. If at all it is not satisfying, then we can add our regular normal non-pre-stressed or TMT rebars to make up for the capacity. So, as you know, the PT cables are usually designed for serviceability, and typically the PT cables, the pre-stressing PT cables is designed in PT slabs for balancing 90 to 100% of your dead load, right. That is the self weight of the slab. So, this is a typical layout with which we find the PT cable, right. But for that we are doing all the analysis. If at all for ultimate condition, this PT cable is also acting as a reinforcement for ultimate strength, right. If it is not enough, then what we do is we are going to put additional non-pre-stressed or TMT rebars to make up for the extra capacity, right. Otherwise, what we can also do is the strength of the slabs can be estimated using yield line theory. Of course, we do not have time to cover that. So, but you can look at the literature how to calculate the ultimate capacity using yield line theory as well, right. So, now we have understood flexure, we have discussed how to use equivalent frame method to do the analysis to get your moments. Now, we looked at how to check for each critical section for flexural capacity. Now, the shear is also important, particularly for a flat plate and flat slab kind of structure. Shear, particularly the two-way shear or a punching shear failure is very critical. In fact, most of the time the thickness of the slab will be governed by punching shear or a deflection criteria. So, anyway, the load carrying capacity of a two-way slab is typically governed by shear rather than flexure, because in flexure we have seen that it is a highly redundant system and the strength and safety is typically not a concern for flexure in a two-way slab, right. So, the failure is actually most of the time it will be governed by shear, and the failure can be brittle if local shear stresses can become high enough to cause a significant diagonal cracking. Now, there are two failure modes. The one is the typical your one-way shear failure mode. So, when you are doing the design strip at a critical section, you can have one-way shear failure, but typically it is not very common, right, especially for a flat plate structure. But however, punching shear, if your thickness is not adequate, because in this region you are not only having shear, particularly for a flat plate, you will also have to transfer the shear for an unbalanced moment, that we will discuss it in the next chapters. And then for a corner column, again it can be, the failure mechanisms can be quite complex. There also they have a potential for failing in corner shear failure, because you have to transfer the quite a high unbalanced moment. So, through shear that can lead to high shear stresses and it can lead to failure. So, these are the typical three, and this is usually not a concern usually not a concern, because as we have seen, in a slab system typically one-way shear is not really a concern, and but sometimes if you have very unusual loading configurations and geometry, it may also play a role, but usually it is not a concern, right. So, punching shear and corner shear failure has to be clear, because at that corner locations again torsional cracking will develop, and we need to put some additional reinforcement to avoid this kind of corner shear failure, right. Now, the shear failure can occur when the incline cracks form due to flexural and shear stresses, and there are two types of failure mechanisms in two-way slabs, particularly in PT slabs. This is a one-way shear where you have a crack, basically it is a beam shear, or they also call that as a beam shear, and we look at it at the face of D from the face of the support, and we look at whether that particular location is having adequate shear capacity or not. And the two-way shear, which is very common in flat plate structure, flat plate slab, flat slab, which we need to check for it clearly, because this two-way punching shear failure can be quite brittle, and typically we take a critical section as D by 2 from the face of the column, and we calculate whether that the area, the entire critical section is having adequate shear capacity or not, right. If it is not, sometimes we also put some shear reinforcement. Shear reinforcement is also provided, and usually these kind of dowels are provided, right. Shear heads or shear dowels are provided, that comes in each strip, that you put it at different critical perimeter to satisfy the additional requirement, right. Now, as I said, the two-way punching shear in a flat plate or flat slab can be quite brittle, and when it is failing, for example, the top negative reinforcement can pull out of the slab, and that leaves the slab with no connection to the column, and the entire slab can slide down. So, this is a very brittle shear, brittle mode of failure, particularly when you have a flat plate structures which are directly connected to the column, and we have to design that carefully. Now, what are the critical sections for this punching shear or a two-way shear? Typically, the critical perimeter is located at the distance D by 2 from the column face, where D is the effective depth of the slab. You can see D by 2, and for circular column again D by 2 we take. For the edge slab, again this becomes your critical perimeter, right. For an interior slab, you have all four sides, you have sections that are resisting the shear, and then when you have a very unusual shaped columns like this, plus shaped columns, then you take D by 2 from all the periphery, and then you create this kind of a critical shear perimeter region for calculating the capacities, right. So, this dashed line is your nothing but your critical shear perimeter, right. Now, if you see here, when you have a flat slabs usually have drop panels as well. So, for this flat slabs, I need to check both at the slab level, I will have two shear perimeters, okay. This is at a distance D by 2 from the face of the drop panel. Also, I have to check whether that particular critical perimeter region is having adequate shear capacity. Also, I need to check at the D1 from the face of, or I should say D1 by 2 from the face of the column, right. So, you have to check at both the locations. As I said, in flat plate structures, again punching shear stress can be quite high, and particularly in the edge columns and corner columns, you have, because you have to transfer a lot of unbalanced moment at those regions. Typically, you may not satisfy the limits, then you have to go for locally thickening and putting a drop panel and so on, and so that it is not going to be concern for two-way shear. Okay. Now, we can also have slabs with openings like this. So, this is the opening, right. Then you, again you take D by 2 from the face of the column, but you subtract that region where the opening is there, then you take this shaded area as your shear perimeter. Similarly, if you look at it, you have an opening at a certain distance, then you draw from center line some distance to the edge of the opening, then whatever this distance has to be excluded in shear perimeter. Similarly, for this location, you have entire opening is here. So, literally now we have only three sides that are resisting the punching shear load, right. So, you have to look at it. Now, another important aspect, for some reasons edge columns, you know that you will have moment at the end joints, or even for an interior column, let us say this is an interior column, if your spans on the left side and right side is not the same, then you will have unbalanced moment. That means, let us say on the right side I have a moment M2, left side I have moment M1, but if M2 is greater than M1, there is an unbalanced moment which is M2 minus M1, that somehow has to be transferred. That can be transferred through flexure of the slab, right. The slab will be subjected, right. So, through bending it can transfer. So, that is what we say, the transfer through bending. So, a portion of this unbalanced moment, let us say this is MUB, unbalanced moment, that can be transferred in flexure of the slab. So, that is MUB that we say, that is gamma times your MU in bending. So, MU is okay, this is MU, the unbalanced moment that will be transferred in bending of the slab is gamma times your unbalanced moment. Now, the gamma parameter can be found out using your column dimensions, that we will explain a little later, right. So, you see here, then what we have here is MUB is gamma into MU, and then the remaining portion of your unbalanced moment has to be transferred in the form of shear. So, how much that will be transferred, the unbalance is nothing but 1 minus gamma times MU. So, this is an unbalanced moment, some of them will be transferred through bending of the slab, some of them will be transferred through shear, which we can explain. So, this is what it is. So, you see here, this is your unbalanced moment that is transferred through shear, which is 1 minus gamma into MU. Now, gamma parameter can be calculated based on the geometry of the column and the effective depth of the slab, and this is given by this, gamma is 1 by 1 plus 2/3 of square root of C1 plus D by C2 plus D. Then you can find out for your gamma factor and then plug in to see how much of the unbalanced moment will be transferred in bending and how much remaining will be transferred through shear. Now, this unbalanced moment can increase the shear stress quite a bit. So, that is the reason the flat plate can have high shear demand, it can lead to failure in punching shear. So, this we need to account for it in a proper way. Now, how that unbalanced moment is transferred through shear? For example, through linear variations of the stresses. Okay. So, you get this, then you get the resistance for this unbalanced moment. So, this is the directions, as you can see, changing. So, the couple between these stresses will give me the resistance for unbalanced moment, part of the unbalanced moment, right. Now, the ultimate shear stress induced by the factored punching shear force at the critical section around the column must be combined with the shear stress due to the unbalanced moment transferred to the column. So, you have one that is coming from factored punching shear force, that we have to include. In addition to that, there is a shear stress that is coming from unbalanced moment transfer to the column, right. So, for the purpose of computing shear stresses at the critical section due to MEV, code actually assumes that the shear stress variation is going to be linear about the CG of the critical section. So, we have seen critical shear perimeter. So, we are saying that this unbalanced shear moment will be transferred through shear, will be having linear variation. So, for example, you have 3 components for a typical shear stress at any section. You have one that is coming from your direct shear punching shear force, which is Vu by B naught into D. Then you have unbalanced moment. Now, see, a joint, a typical joint will have frames in the x direction and the frame in the y direction. So, this is the unbalanced moment in shear in the x direction, and C is your distance of the point under consideration where you are calculating the shear stress on the face of the critical section to the centroidal axis. From the centroid of the critical section in the extreme face where we are doing the calculation, that is C is a distance. Something in bending we say y, typically at the extreme fiber, right. So, similarly, the extreme locations of your critical perimeter where you will have high shear stresses, that we have to take. In addition to that, we will also have shear, again the unbalanced moment in shear has to be transferred in the orthogonal direction. So, that also has to be included. So, that is the reason your shear stress at close to the column can become quite high if your unbalanced moments are quite high. Okay. So, how do we calculate these sectional properties? You know, this is JC is nothing but your property of the critical section analogous to your polar moment of inertia that we have studied. So, for this particular section, if you look at it, for this column dimensions is taken as C1 and C2. Now, my critical perimeter is going to be C1 plus D by 2 on the left side and D by 2 on the right side. So, my dimension A will be C1 plus D and my dimension B will be C2 plus D. For this one, now for the entire depth, effective depth, you know, you are looking at the plan view, right. So, now the sections on all the 4 sides is going to resist. So, for that, I have to create the geometry. Now, the geometry, the polar section is nothing but your A into D cube plus A cube into D by 6 plus, just like similar to your parallel axis theorem. So, I have to also calculate area of the section times A square by 2, because now I have to take 2 of them, right. So, that is what we are calculating. So, because here your distance from this C in this case is going to be, for example, C, the maximum distance here is nothing but your A by 2. So, C is going to be half of A, which is A by 2. This is for an interior column. Now, how does this thing happens for an exterior column or an edge column? You can see here your shear perimeter now will have only 3 faces, right. For this, again we can calculate the centroid, and the C distance will be A square plus 2A plus B. Using simple geometry, I can calculate these distances, right. And then the polar moment of inertia, the sectional property can be calculated using this. Similarly, we can also do it for a corner column, right. So, this is one example for an interior column, one example for an exterior column, and we can do the same thing for a corner column as well. So, the whole point is, it is just not the direct shear that is coming from a punching shear load. We also need to include the unbalanced moment transferred through shear both in the x direction and y direction. So, that is going to increase your shear demand quite a bit. So, that we need to be aware of that. Right. Okay. The polar moment of inertia, I think you can see that we can calculate for this particular interior column geometry. Let us say this is B1 and B2, the critical perimeter width, and your effective depth is D. Then JC is nothing but Ix plus Iy plus the area into distance square, right. So, now the areas you can see here, if I am talking about one axis is, which will be B2 into D, because if I am talking about this axis, right, the axis is passing through this B1, right. So, polar moment of inertia is going to be d B1 cube by 12 plus B1 d cube by 12 plus these sections are at a distance of B1 by 2, right. So, in this case x bar is going to be B1 by 2. So, I can calculate that x square is, you know, using that I can calculate my overall section property JC like this, right. So, now what are the shear stresses due to V? We have said that it is going to have a linear variation, and gamma V is a factor that depends upon the thickness of the slab and the column dimensions, and C is the maximum distance, the edge distance from at the locations where you are calculating the shear stresses, right. This is coming from your unbalanced moment in shear. Now, in addition to that, you also have a direct shear stress, which is due to the applied shear force, which is Vu, right. So, you have to add them up, this plus this will become the total shear stress. So, some locations you can see the shear stresses can become quite high. So, these are the total shear stresses. That is why we have to look at the contribution of your unbalanced shear as well in the calculation of your shear demand, right. Okay. So, finally, this is the overall expression for calculating your shear stress. This is from again unbalanced shear in the x direction, unbalanced moment in shear in the y direction, and these are your B naught is the perimeter and JC is the property of the critical section analogous to polar moment of inertia, and C is the distance of the point under consideration on the face of the critical section to the central axis, right. So, we have explained it in the previous slides, right. Now we have talked about the shear demand. Now, how do we estimate the capacity of a flat plate, right. So, again our code gives you an expression which is Ks times tau c. Tau c is the value that we have seen, which is taken as 0.25 square root of FCK, and you also include the effect of your axial. This is coming from axial component of a field stress. Okay, this is vertical component. And when we talked about shear chapter, when we discussed, there is also going to be a vertical component that is going to reduce the shear demand, or we can either you can include it for reducing the shear demand, or we can include in the capacity. Here it is included here. So that can also be there, but you have to estimate it in a correct way. And there is also one more factor called K factor, KS factor, which is giving you this 0.5 plus beta C. Typically it has to be taken less than 1, where beta C is the ratio of short side to the long side of the column, right. Depending upon the geometry of the column, then beta factor has to be there, but anyway KS cannot go more than 1, right. You see here the tau C now has to be 0.25 square root of FCK, and average pre-stressing force in a PT slab, you know that we have discussed in the last module as well. Minimum is 0.85, optimum ranges from 1 to 2 megapascal. So the average pre-stressing force is going to be between 1 to 1.5 megapascal, and B naught is a perimeter of the critical section, and D is your effective depth, and initially for initial checks you can take it as 0.8 times the overall depth, and VP is the vertical component of pre-stress that I think we will discuss how do we get that. We have discussed this in the shear chapter, but again quickly we can show how this VP component can be added. So we have to add all of them to get your overall punching shear capacity of the slab, right. So again we have seen, and now what we have to do is this the shear capacity. So now this B naught into D. Now how do you get your B naught? B naught is your perimeter. So the perimeter is C1 plus D, D by 2, D by 2. Similarly C2 plus D. So C1 plus D into 2 plus C2 plus D into 2. Then entire thing has to be multiplied by D to get the overall area, the shear permitted area that is helping you in shear resistance for punching loads, right. So this way we can calculate, and that is why this B naught D. So a perimeter multiplied by effective depth will give me the overall area that is helping in resisting your punching shear. Okay. Now the vertical component, we have seen that close to the support you will have this kind of a reverse parabola, and we know that the vertical component is proportional to the slope change that it is happening from the cable profile, right. So for a parabolic cable profile, you will have each location, you will have a unit vertical component that it will come, right. So we are looking at what are the effect on the concrete. So the VP is going to be acting down here, right. So that is proportional to, basically we are multiplying for the entire perimeter distance, which is C1 plus D here, because this is C1. My perimeter length, for example, critical section is going to be C1 plus D by 2, C1 plus D by 2. So I have to integrate what is the net vertical component that is coming over this distance of C1 plus D. So that is what we are doing here. Now what is the unit vertical component that it is going to come? And if I assume my the length of the cable profile is 2 times beta L1, right, then we can find out what is the slope change that is happening, then multiplied by the pre-stressing multiplied by the slope change will give me the unit vertical force that is there due to pre-stressing, then multiplied by the length will give me the total vertical component of the pre-stressing, right. So this has to be, this is the radial force that we talked about. Now however here the small changes in the tendon profile will subsequently affect the value of VP. So whenever we are estimating this VP, we have to do it in a very conservative way, but it is not going to be small also. So you can take advantage of this VP to optimize your design, but at the same time these profiles have to be calculated properly, and this VP component also has to be calculated in a conservative way. So finally when you do all those things, you estimate your capacity, or VUR I should say, right. So the demand has to be less than your capacity, right. So this is what we said, the radial force, it comes from your slope change. This finally will work out to be 2 into P into H2 divided by beta L1 whole square, right. So from here I can find out what is the vertical component force. Okay. So in this part of the module, we only explained the theoretical basis for equivalent frame method, and then we also looked at flexural and shear considerations, right. So, in the next 2 parts, we are going to go through a detailed example step by step how you design a PT slab and also how you compare your equivalent frame method analysis with your safe results, which is your commercial package. So, let us conclude this part. So, we have discussed the concept of equivalent frame, we have illustrated various components of equivalent frame, we also discussed the steps for analyzing the slab using equivalent frame method, and we also discuss the considerations for flexural shear capacity calculations for a PT slab. So, with this we are completing this module. So, we will continue in the next week. Thank you.